Services Club and ZN. It's a pleasure to present this update on the post-quantum cryptography problem and our report from last year. Our report focused on how this problem affects blockchain and smart ledgers, but similar concerns apply to any financial services company that uses encryption, which means just about everybody. Today's presentation includes some technical developments since our report was released, but the overall message remains exactly the same. And that's good news. It means that there have been no major surprises in quantum computing development in the past 18 months, although there has been some progress. This presentation is about risks that will happen over a longer term, that will cause network security after about 10 years from now, and more likely 15 to 20 years from now. But these are major risks, and ones that may require action now for some reasons that I will explain this morning. Fortunately, though, they are manageable risks for those who pay attention to them. So, large-scale quantum computers would pose a serious threat to the security of public key cryptography. So, what should effective entities do and when? I won't just read all my slides, but this is the agenda for my presentation, and it's a good summary of our report. But while the issues can be stated briefly, there's a lot of technical detail behind them. Explaining that detail at a high level is what I plan to do in the next 20 minutes or so, and there's a lot more detail in the report. The numbers in circles on this slide indicate the order in which I'll unpack this summary, starting with an explanation of public key cryptography. To understand public key cryptography, we'll start with the state of the art before it was invented. This is a German Enigma machine on the left, and on the right is a bomb computer at Bletchley Park that was used to break Enigma, as portrayed in the movie The Imitation Enigma used symmetric cryptography, where both the sender and the recipient use the same secret key. This posed problems of key exchange. For example, at least 2 captures of Enigma secret key sheets on German vessels were instrumental to breaking Enigma. One of those a ship, one of those a submarine. There may have been others. Also during World War II, plane loads of key material need to be transported by the Allies into various locations in theater so that everybody would have the secret keys in the right places. And this kind of symmetric cryptography was essentially the state of the art for secure communication until the 1970s. In the early 1970s, public key cryptography was invented here in the UK by James Ellis at GCHQ, that's Government Communications Headquarters in Cheltenham. Although apparently it was never implemented in its initial form, and it was not disclosed until a decade later. But in 1976, Whitfield Diffie and Martin Hellman published a paper on a key exchange algorithm using public key cryptography. Now, what is public key cryptography? What it does is it uses public and private keys for each communication, which avoids the need for key exchange because all the core applications can be done with a public key that can be made available to anybody. This seems like magic to the uninitiated somewhat. It's based on what are known as hard mathematical problems or one-direction problems. One example is the knapsack problem, that it's easy if you have a bunch of weights. You throw a bunch into a knapsack and figure out what the weight of the knapsack is going to be by adding them up, but if you know the weight, it's a lot harder to figure out which of the weights have gone into the knapsack. A much more common hard problem for our purposes this morning is the integer factorization problem, which is you take 2 very large prime numbers, multiply them together. The multiplication isn't that hard to do, but taking that even much larger product of the 2 numbers, figuring out what the 2 original primes were, is a very hard problem. And this technology secures many aspects of electronic communications and authentication. The locks on the top right are an illustration of how this works. You can think of it as, if you want to send a secure message, you take your public key, which is the open lock, and put it all over the world. And that effectively means publishing it on the internet. Then anybody can take that lock, attach it to a message, and send the message to you. But you're the only person who can open the message by putting your private key into the lock. That's the essence of secure communication. So looking at the chart at the bottom, if you want to do public key secure communication, the sender uses the recipient's public key, and decrypts, and the recipient decrypts the message with their own private key. Only the recipient can read the message. Public key cryptography also works for another very important application, which is digital signature, to authenticate that something was done properly. And there it's reversed. The sender uses their own private key, and the recipient uses the sender's public key to verify that it was the sender that signed. And the math is such that only if the sender used their own secret private key will it be verified with the public key. It's a little bit complex, but hopefully that gives an idea of how it works. So, before we talk about the risks to public key cryptography from quantum computers, we need to understand what a quantum computer is. So I'll first explain briefly how quantum computers work, number two, and then discuss what we mean by a large-scale quantum computer, that is, one powerful enough to cause problems for public key cryptography. There are two key quantum phenomena at work here. One is called superposition. So in a classical bit in a computer, every bit has the number 0 or 1. In a qubit, which is the equivalent of a quantum bit, a bit simultaneously has all states between 0, 1, and any value in between. The other key phenomena is entanglement, which is that two quantum particles, can be entangled even though they are not near to each other. So they get entangled, and then they're separated, say between London and Paris, is the example we have here, but they still behave as if they're connected to each other. Now, Albert Einstein, in the day, didn't believe that this made sense, and it seems kind of weird still. He said of superposition, God does not play dice with the universe. He said of entanglement, but called it spooky action at a distance. But the bulk of the scientific community now accepts that these quantum phenomena are real, although some think that they may have explanations in classical physics. For our report, we tried to interview Ross Anderson, who's one of the UK's leading cryptographers, and we interviewed a lot of great people, but Ross would only reply by email. He wouldn't have to do with a quantum report because he doesn't believe quantum computing is real. And Michael made the comment, is this like fusion that's never going to come? Some people still think that, although the majority of the scientific community seems to think that there's something there. So assuming that these phenomena are real, if you link together multiple qubits through entanglement, the two phenomena we're talking about, you can simultaneously explore all the states of any combinations of the qubits. So 10 qubits provides about 1,000, 2 to the 10th power, different states. 64 qubits, the parable of the chessboard, the inventor of the game of chess supposedly was asked by the Emperor of India what he wanted for inventing it, and he said, I'll take a grain of rice on the first square and 2 grains on the second square, and so on. That turns out to be about 18 quintillion grains of rice, which is about the size of Mount Everest, and 1,000 times annual global rice production. And that's the number of states that you can explore with 64 qubits. But on the next slide, we're going to be discussing thousands of qubits, which means a much, much bigger number that you can explore simultaneously if these quantum computers work. So quantum computers were first proposed by Richard Feynman in 1981, not to solve a particular application, but to demonstrate quantum effects, to simulate quantum effects. It was a long time until there was any progress with entangled qubits, as what I just described. The first entangled qubits, the minimum entanglement is 2, was not until 1998, 17 years later. By 2011, we were up to 14 with academics in Austria and Canada, and the way it's tended to go is now the big tech companies are doing it, so it's Google and Intel and the like who are building the largest quantum computers. Now Google announced a machine last year with 72 entangled qubits. So there are 2 kinds of qubits. There's a distinction between physical and logical qubits that we need to talk about. Physical qubits are the numbers above. They're low-temperature devices showing quantum effects with entanglement. But the trouble is that this entanglement falls apart really quickly, about 100 microseconds, 1/10,000th of a second, for the current operational quantum computers. And that means to build a logical qubit. A logical qubit is a qubit that sits there and lets you compute, like a bit in a current computer. To build a logical computer, you need a lot of error correction with a lot of underlying qubits that are constantly falling apart. And the current estimate is that you need, there aren't any logical qubits yet. The current estimate is that you need about 1,000 to 10,000 physical qubits to get to one logical qubit. And as I'll repeat on the next slide, you need about 3,000 to 5,000 logical qubits to attack current public key cryptography. So that's somewhere between 3 million and 50 million physical qubits, and we're now at 72 to get to be able to attack current public key cryptography. So these things tend to progress exponentially, but we're really some distance away from a real threat at the moment. So, what is the threat? You know, when I was in school, they talked about the new math, which was a new approach to learning addition, subtraction, multiplication, and division. But this really is new math. It's a completely new area of math. The algorithm that got everybody excited about this was called Shor's algorithm, discovered in 1994 by Peter Shor at Bell Laboratories, part of the old AT&T system. And this algorithm, which is too complex to explain here, would allow a sufficiently powerful quantum computer to quickly solve the hard problems underlying the most common public key cryptography algorithms. And some of these are RSA, elliptic curve digital signature algorithm, and Diffie-Hellman. RSA is commonly used for web connections. ECDSA is the standard algorithm for blockchain signatures. And sufficiently powerful is estimated to mean, as I mentioned on the last slide, about 3,000 to 5,000 logical qubits for the current length, the current strength of RSA, called RSA 2048. Now, you can strengthen RSA pretty quickly, pretty easily to make it 4096 or even bigger. But once the quantum computers go exponential, all of these things will be solvable if the quantum computers can do that. There is another algorithm that's considered a threat. It's called Grover algorithms. It was discovered by Love Grover, also at Bell Laboratories a couple years later. It provides a quadratic speed up, which means that if something takes x squared time now, it would take x time with this algorithm. And that's for attacking symmetric cryptography, which we discussed earlier, like the Enigma algorithm, and hash algorithms that are used for authentication. That is a much smaller threat, though. A quadratic speedup is pretty significant, but the Shor's algorithm speedup is much greater, and it's actually easier to secure symmetric cryptography. But there are good alternatives that avoid these threats. So, what should we do about it? And I will discuss the when about what we should do before the what, for reasons that will become apparent. So, Michele Maaske is kind of the guy in this field. He's at the University of Waterloo in Canada. He's a mathematics professor, cryptographer, and quantum computing expert. He's the founder of Evolution Q, which is a consulting firm that addresses exactly this post-quantum cryptography problem. We interviewed him for the report. He was a very nice and helpful guy. He has formulated something called the Maaske Inequality, which is, as it says on the slide, you have three values. X is how long you want your security to last. Y is how long it takes you to replace your cryptography. And Z is the time until quantum computers are available, which is estimated to be probably not less than 10, probably not less than 15 to 20 years. Sufficiently powerful quantum computers is what is currently considered to be the rough minimum. So if x plus y is less than z, there is still time to act. But if x plus y is greater than z, then it may already be too late to entirely avoid the post-quantum cryptography problem. And for some systems, it's possible that they fall into the second category, especially where x, the desired duration of security, is very large. So some examples: blockchain and smart ledgers, life insurance policies, certain long-dated bonds have desired security periods that are greater than 20, 25 years. So if it takes 15 years for the quantum computers to come along and a few years to replace it, then you're already in the situation that you should have been doing something about it now. There are other financial services examples where clearly there is not a problem. So e-commerce transactions, which is most of what is secured by these things, probably don't have a security concern in most cases above a few months. If it's the credit card element of it, most credit card companies reissue their credit cards every 3 to 4 years, and so the numbers will expire. So, you know, for credit card transactions alone, this is not yet a problem. There's time to fix it. So, what should we do about it? Well, as Michael said, don't panic. In the report, we hypothesized the images here that the dichotomy between Chicken Little, this is an old Chicken Little cover running about saying the sky is falling, or don't panic as it says on the cover of the Hitchhiker's Guide to the Galaxy. And we think, as Michael said, the answer is don't panic. Michael talked about the Y2K problem. Is this like the Y2K problem? Maybe a little bit, but there's no certain deadline for this problem. Like Y2K had a very precise deadline, although some things happened before the year 2000 hit. Maybe it's more like climate change, because it has uncertainty both as to timing and as to impacts. Climate change is one problem that, unlike quantum cryptography, the consensus seems to be growing rapidly, that it's becoming an increasingly severe problem. The same may happen with quantum cryptography over time. So, but good solutions are coming to address the problem. There was an EU project called Key Cryptography that came out with recommendations for secure algorithms that will be secure against quantum computers. That was in 2015. And the biggest game in town is the US NIST, National Institute of Standards and Technology, has a competition that they launched in 2016. We interviewed the guy who's running the competition, Dustin Moody, he's called, nice guy. And NIST has been behind a lot of the current default encryption algorithms. There was another competition that led to AES a number of years ago. 69 submissions were received from cryptography groups around the world early last year, around the time of our report. Early this year, round 2 candidates were announced, 17 public key confidential algorithms and 9 digital signature algorithms, and they're now going to set out to test those, narrow it down, see which ones work and don't work. When we were looking into this last year, the view of NIST was that this project, the competition is likely to conclude around 2022. I'm not aware that that has changed. There are quite a lot of avenues towards secure post-quantum cryptography. Each of these is quite technically detailed. This is a list of some of the technologies that are used for quantum-resistant algorithms. There's a small amount of additional detail about this in our report, although the technical detail of this is really quite substantial, well beyond the level of technical detail that I've been talking about today. So, last slide before I pass back to Henry and then the panel. What sort of program of action might one have? And this is a flow chart of how we think companies might go about it. First, decide what resources you need to address the problem. You need the people who understand it, and that could be internal resources or external, people like us who understand the problem. And then monitor what's happening. Monitor the development of quantum computing, monitor the development of solutions, and then assess, based upon what's out there and having the right people who understand it, what the quantum risks are to your particular systems. And there's a feedback loop because the risk assessment affects what you need in terms of resources and what you would monitor. Then based upon that assessment, plan what to do. And that also gives feedback to the earlier steps, depending what plans you decide. And then once you decide what to do, implement it. There is one, this is not a specific recommendation for particular action because it depends heavily upon the nature of particular systems. But there is one conclusion that seems fairly obvious, that new systems should be quantum resistant from the start to avoid the risks and costs of re-engineering. Now, if you really don't believe quantum computers are coming, maybe you don't do this. But for substantial systems, it's an awfully good idea. However, many new systems are not taking this approach because most familiar off-the-shelf components like RSA, which is the most common algorithm for securing internet connections, are not quantum resistant. And that may not be a problem if you're running a website where the most you have to do is secure credit card transactions and you're using the public standards for that. But if you're doing something that requires building new systems, thinking about the post-quantum cryptography problem is a good idea. Thank you.
Thank you very much, Maury. As you know, Maury has gone through at a rapid pace, but I think very clearly and simply what we're facing. The report that he's done is either on your seats or available outside, so there's more to read later, so if you feel you need a bit more detail, it's there. Now, we've asked Henry to make a bit of a response. Henry's a doctoral candidate affiliated with the Theoretical Physics Group and the Center for Complexity at Imperial College. One of the reasons we're asking Henry is one, to get a view probably from somebody who's fairly aware of what Y2K is. But Henry also has a wide range of interests, and that includes some things like quantum gravity, the application of digital humanities, for example, in archaeology, derivatives and futures contracts on Bitcoin, but also, of course, quantum computing. So he, like Maury, has got that great span that I think this sort of problem requires. Henry, your thoughts?
Yes, I'll keep it to just 2 points because I don't want to. Well, I'm going to have plenty of time for questions, and I'd like to thank Maury for his good report and also Manelli for giving me a chance to talk. So 2 points. What's complexity? I think I'll call it that'll do, something like that. And then a problem shared is a problem halved. So basically, complexity is kind of talked about here. So it's sort of how hard it is to do something and then how long it takes to do it. And it's kind of, if you read all the papers coming from sort of 60s, 70s, you're going to say, if there exists a one-way function, and it's like, okay, what's a one-way function? It means I can't go back, so whenever I take this thing, I can't reproduce it backwards, which is basically what encryption is, And then you kind of say, well, based on the intractability to solve the elliptic curve stuff, so kind of based on this, there's a lot of assumptions in cryptography, basically from the beginning, from the outset. So, that'll do in the sense of it's good enough. So, based on all these problems, you've got to think, oh, when do I really need to kind of take action is based on how secure I want my system to be, which I'm kind of encrypting. For example, there's been a few number of high-profile cases to do with, message digest 4, which is the same as a hash function, but it is a hash function, but they call it message digest 4. To do with passwords and stuff, and essentially, they're kind of irreparably broken, but they're still actually used for quite a lot of password stuff, including a couple of high-profile hacks. And more recently, with hacking, so let's go back to one-way functions. They then say, okay, well, if there's a one-way function, I can create a pseudo-random number, which means, given a seed, I can produce a thing on the other side, which I can't tell what you did, but it looks random to me. And essentially, it looks random to me is what cryptography is. So you kind of say, okay, well, pick the random seeds. And there's a big trivial hack on Ethereum recently where people were basically just trying, seed 1, seed 2, literally put the number 2 in, put the number 3 in, put the number password, as it were. And a lot of their cryptography became insecure purely by the fact that we exist this one-way function, and it's not random, it's pseudo-random, and you can get to the thing but you can't get back. But if everyone is putting the same input in, you get the same answer. So then this kind of moves on sort of asymmetry. I would say complexity asymmetry is one of the main things which you touched upon with the prime number problem. So with the hashing, you see, it's very, very hard to do, so it's kind of computationally exponential to get it, but it's kind of log order to search. So it's kind of, this huge asymmetry kind of gives you certain properties, which is what they use for the hash, the rewards in blockchain technology. So I bring it back to ledgers and blockchain, which is what I know. So it's very hard to produce the hash at that level, but actually, it's trivial to check. It's just a one-way function. Get my answer. And then the second point I'd like to make, because I actually came from quantum gravity into crypto, which is via directed acyclic graphs, which is the linear cases of blockchain. So a problem shared, a problem halved is you have technologies to do with hashtags, and IOTA being one of them, not not that they're necessarily the best one, is they kind of split the block up. So you know how we talked about the square root of n. So now I'm saying, okay, well let's split these guys up so they're in one big n. I have 2 of these n's. So let's do a numerical example where you kind of say, okay, well, I've got a 16 operation function. Because imagine this is what complexity is kind of measured in. I square root that, I get 4. Do I? That sounds good. And then sort of 16 is 8 plus 2. So the square root of 8 plus 8, that's about 2 point something. 2.34 plus 2.34 is much greater than 4. So if you divide the thing up and square root it under lots of little problems, it's still the same difficulty to break. So if you stay in that space, it's a lot more powerful. So there's a lot of people, if kind of last resort, let's break the problem up and make you do the thing multiple times. Because under small n, obviously the square root function kind of grows like that rather than in a straight line. So the smaller you can keep these things, but divide them up. So basically divide your Bitcoin into little bits and then hack each one is a lot harder than just hacking the big thing. There's recent research from Imperial saying, one of my friends, there's about 10%, 20 plus another 23% of exposed public keys on the Bitcoin blockchain, for example. So those, if you have that out there, the private part can be inferred. So those are preferably under attack. And there's a few countermeasures called like proof of delay, where they kind of point back to the past because you can't unravel time, as it were. You can't uncrypt time. And a few other exotic proofs of stake and proofs of I guess proof of state, I would call it. They could also prove an answer without having to go redevelop all the quantum cryptography, which the report covers very well. And in addition, I would say that the hash is not the big problem. It's the private key. So the private key, public key cryptography. The hashing is already kind of very optimized with ASICs and ASICs, what we call them. So, but that's a problem for everyone, like Melanie said. So that will be the problem. But thank you very much.
Thank you.